Good morning and welcome to the course on smart materials and intelligent system design. Now, in the last module we have talked about smart materials. So, we have talked about in the very last lecture about the shape memory effect, metallic alloys that show shape memory effect, one way SME, pseudo elasticity, two way SME and applications of shape memory alloy. So, after the review of all the smart materials, now we will talk about composite materials. We will give you a brief introduction about the composite materials. So, what is the requirement of coming back to composite materials? Some of you might have actually gone through this in my course on nature and properties of materials. Now, smart materials and composite materials, these two are integrated with each other, and that has happened not just today, but something like last 30 years. This is the effort that is continuously happening in this domain. Now, why is these two concepts are so close to each other? Well, if you remember that in the very definition of smart materials, I told you that it consists of three things. It has sensors, it has actuators, and it has some microprocessing capability. So, a best example of any smart material will have all these three things. Now, you remember that if you take any system, say suppose if you want to develop a structure which has these capabilities, then where will you put such sensors, actuators or microprocessing? You will put it on the structure. So, the moment suppose I am taking a cantilever beam which can be representative of so many things, okay, starting from the helicopter wing, aircraft wing, so many things. Now, if I put a sensor here on the top or an actuator here on the top, then until and unless it is not totally integrated into the host structure, this is the host structure, it will not work functionally well, because all these parts will be actually subjected to the ambient conditions. And you remember that think of it that suppose this particular system is working at a high altitude or at high temperature, etc., then these sensors and actuators will be inoperative, because you have a Curie point limitations. So, the best strategy towards designing any intelligent system is that suppose if you have such sensors and actuators and you want to integrate it, now I am just magnifying the whole thing, we embed these things inside the system. So, this is embedding. So, this is surface bonding, which is not very functional, surface bonding, and this is embedding. Now, the moment we embed these sensors and actuators, what happens? This becomes composite structure, because it would start to contain many of these different types of materials inside it. And not only that, the question is once you make such composite, the what scale, at what scale you are making this composite, at what scale? Well, one of the directions that we take is that we reduce the scale to as low as possible, so that we can increase the degree of integrity of all these sensors, actuators, microprocessors with the structure itself. Take for example, the case of shape memory alloy, which you have just studied. So, I have suppose the same beam whose shape I want to control, and instead of putting the wires outside like surface bonded, suppose I am keeping these wires inside. Now, this is one way of actually accommodating SMAs in terms of a just like a continuous fiber, the way we do it in terms of composite materials. But in order to activate such SMA continuous fiber, SMA as continuous fiber, you need to have power supply. Now, the moment you give this power supply from outside, the integrity of the system is lost. Instead of that, suppose if you have a composite and in that you have a layer, and that layer is made of carbon fibers and some chopped SMAs. So, you have very fine even you can go up to so fine SMA in carbon fiber reinforced composite. What will be the advantage? The advantage will be that the carbon fibers will increase its conductivity, and hence you can directly actually apply the current on the carbon fiber from some source, and the moment you apply the power on the carbon fiber, it is getting heated up, and that heat is transmitted to these shape memory alloy based chopped wires or even fine nano fibers of shape memory alloy wire, and it will actuate the whole system. So, as we are going to finer and finer scales, So, what happens is that we are going to get actually composite systems all along. Okay. So, that is what brings us to the realm of composites, because we need to have some ideas of these composites in terms of modeling such systems. So, today I will first give you a brief introduction to composites and smart composites. We will then talk about some classifications of composite, composite applications and some fibers and their types. In subsequent lectures, I will talk about the mechanics of such composite materials. So, what is a composite? We all know that in order to make a composite, you need 2 or 3 materials to be mixed at a micro to macro scale, depending on what type you are developing, but you must ensure that in this mixture there will be distinct phase or constituents, and this mixture then may consist of all our known classifications of materials like metals, polymers like ceramics. All of them you can mix and match depending on whatever is your requirement. Now, when we are mixing this, we have a primary engineering goal in mind, that you want to achieve a better balance of properties from the combination of materials. So, this definition also will alert us that what we cannot consider to be a composite. Like if you use some fillers that is indeed used in plastics like plasticizers etc., then it would not become a composite. You need to have distinct mixture of some significant ratio in order to have composites. If you develop some alloys which is macroscopically it is not heterogeneous, that means it has some kind of microscopic bonding etc. in it, then we cannot consider it to be a composite. So, from that definition, shape memory alloy itself is not a composite, but if you put the shape memory alloys inside a polymeric system or any other system, then it would become a composite. Metals with impurities, same reason you cannot really consider them to be composites. So, that is what alerts us about that what we can consider as a composite, where you are having 2 or more distinct phase or constituents, and those which are not actually chemically bonded, but macroscopically from the physically there is a interaction that is there between the phases. So, that you can achieve a better balance of properties, you can achieve say for example, higher strength, one of the objective always invariably you can achieve say for example, higher elastic modulus, you can achieve just now I have given you the example of shape memory composite, you can achieve higher conductivity, thermal conductivity or electrical conductivity. So, this kind of objectives forces us to make a composite system. So, is just the repetition of what I told you, that in the domain of composites we have polymers, we have metals, we have ceramics. Okay. And if we consider smart composites, then we have one more here which will be interacting with each one of them, little less in terms of the metals. So, and more in terms of polymers and ceramics. So, I am keeping small overlap with the metals. Of course, SMAs are there, but this can be smart materials. So, then our domain will be complete in terms of smart composites, if we want to think of it. So, and another point is that in any such composites there will be matrix and there will be fibers, and you see there are distinct interfaces between these fiber and the matrix. So, this is reinforcement or interface. Interfaces are actually reinforcements, very popularly we call it, and there is a distinct interface between the two. There are some classifications of smart material in terms of, I would say, smart composite material. What are these classifications? There are basically 3 groups. Group A is called sensible materials, which are just embedded with sensors that can sense the change of environment. Okay. Let us say I have a composite and I have added some optical fibers in it. Okay. One of the examples, right, say this carbon fiber reinforced plastic, we will talk about it later on, but this name is very important, reinforced plastic or polymer, CFRP, and that if I add with that some optical fiber as a intrusion of a smart material, what it can do? It can actually sense that the curing process, how the carbon fiber is how the polymer in which the carbon fiber is kept, how it is getting hardened. So, it will give you this process. It can also talk about give us information about the evolution of fractures etcetera inside the system. So, this kind of smart composites are called sensible smart material based composite. One degree further is actually adaptable. In this, if these are integrated, they can actually help the host structure to change its characteristics. Let us say they can help the host structure to get to change its modulus of elasticity, or to change its geometric shape, or to change its stiffness, or to change the viscosity in some cases. So, all these things are actually in the category B, that is adaptable. So, you can more or less think in this manner that A is related to sensor and B is related to actuator, group B is related to actuator, and finally, group C. Group C are the adaptive ones, which can not only sense or not only actuate, but it actually after collecting the data process the collected data and then react. So, that is the maximum degree of smartness that you can achieve, and this is intelligent system. So, that is the kind of classification that we are talking about, and you can see in each one of these cases, as I have discussed with you earlier, you have to develop a composite in order to give these kind of features to the system. There are couple of examples I want to give you in this respect. The one that first comes to my mind is the macro fiber composite. As I have brought a sample for you from laboratory. You can see this macro fiber composite here, and you may be able to see very thin lines inside, and also in the two sides you can see that the electrodes are there, and these thin lines that if you are able to see is these are actually the reinforcing active fibers that is there in a macro fiber composite in this whole system, and you can see how flexible this whole system is. Okay. So, that is something that you cannot achieve with a piezoceramic material simply. So, by applying voltage we will show you that this will start to actually vibrate like this, and that will impose vibration on a composite system. So, that is something that you can see in this particular small video from the laboratory, where you can see that how this macrofiber composite, you can see how it is surface bonded. In this case you can also embed it, it is expensive. So, I have just simply surface bonded it, so that we can use it for many different purposes, and you can see that this is a composite beam made of glass fiber reinforced plastic, and we have two power lines from here. Okay. And what we are doing, we are going to apply an alternating voltage in the system. As I am applying the alternating voltage in the system, and as I will be gradually increasing the amplitude of the voltage, you should be able to see that the vibration will be coming out on the, you can see that already as I am increasing the voltage, the amplitude of vibration is gradually increasing on this composite beam. So, by further increasing the voltage, you can increase it to a even more vigorous level. Okay. That talks about the power of this simple system, so nicely integrable to a system. Okay. So, this gives you some idea about the power of the composite material. So, this is macrofiber composite, and let us look into some of its properties. That what it essentially consists of is piezoelectric fibers, and you can use it both as sensor as well as an actuator. So, these piezoelectric fibers are sandwiched between layers of adhesive and electrode polyamide film. So, this yellow color that you have seen is because of the polyamide film, and when you embed it on a surface, embed it in a inside or bond on a surface, so to say, or attached to the flexible structures, this MFC actuator will provide you distributed deflection and vibration control. It is basically developed at NASA Langley Research Center. The key technology here is to actually get these active fibers that is there inside this. Then actually we can also make such a system, but to do it in a micro scale is something for which you need a high precision laboratory. So, this is one of the example of a smart composite. The other example, I was talking about shape memory alloy. What I have not told you is that shape memory polymers, SMP we call it, they are also a very interesting group of materials which can actually, they are naturally composite, you can say, and that can remember not only just one phase change, that is if you know that for SMA it is between martensite and to austenite, right, high temperature phase. But in the SMP there are, and this is what is our phase transition temperature, right, phase transition temperature. But for the SMPs, this is SMA, for the SMPs what you are going to see is that there are many such phases. Let us call them as phase 1, 2, phase 3, etc., and each one of them has a typical temperature, we call it as glass transition temperature, in which the polymer change its basically form in terms of the motion of the polymeric chains or the arrangement of the polymeric chains. This is is the by the glass transition temperature defined. So, the advantage is that instead of getting one or two, you can actually generate many shapes in these materials, and much unlike their metallic counterparts, these materials are cheap. They possess multiple memories and lighter in density. One example I have given you, which is coming up very nicely, is a light operated SMA. So, this is a light operated SMA system, and you can see that in this system you have actually optical fibers inside, and these optical fibers carry the light that actually increases the temperature, and because of that slight increase of temperature from 28.8 to 31 degrees centigrade, you can see that the shape memory polymer starts to work. So, these are fantastic examples of such things. What are the advantages of these systems? Already I told you, but let us put these points in our mind, that strength is one of the advantage, electrical conductivity, modulus, fatigue, thermal conductivity, weight, resistance to wear, resistance to corrosion. These are some of the things which particularly comes from passive materials as reinforcements that you put, behavior at extreme temperature, acoustical insulation, vibration damping or vibration actuation. I have shown you using MFC how you are doing it, bending actuation same, and sometimes the aesthetics also, particularly the electroactive polymers EAPs. They are these days used for many such aesthetic applications. What are the critical issues here? Okay. We have to cross some of these hurdles when we will be actually modeling this system. The first and foremost important issue is the anisotropy, because a large number of composites have direction dependent material properties. Say for example, in this particular case with this particular composite system, we have shown the fibers. So, fibers, this is the fiber direction, along this direction it has a different property, and along this direction the transverse direction it has a different property. So, the anisotropy is a very important aspect, this is the most important one. Secondly, sometimes we cannot really control the process, like if you think of chopped SMA fibers or any such chopped fibers, then you cannot control how it is distributed. So, it will become non-homogeneous. So, that is a second critical issue. Well, cost of course, in some cases will be really important, particularly when we are developing systems which will be for mass use. Then there are difficulties to fabricate. I told you that some of them at a very small scale it is very difficult to fabricate. They have sensitivity to temperature very much. The usual polymers itself degrades because there are polymers there. So, the composite polymeric composite itself degrade. Further to that, if you have smart materials, some of the smart materials will suffer from the Curie temperature. So, it has the sensitivity, and then of course, the moisture effect, because laminated composites are in general sensitive. So, that will you have to consider while modeling such systems. Now, there are various applications of it. For example, the commercial aircraft, where you have low risk, low cost composites in the wings like McDonnell Douglas or Boeing, they heavily use these composites. Military aircraft use it for that sensible sensitive systems that I told you earlier with intelligent sensor materials, stealth materials for example, and then low observable, these are the stealth materials. This is also known as stealth technology. This is used in F-117A if I recall, as a stealth bomber. Then aero engines and all these actually are some of the applications in aerospace. There are other transport applications also other than aerospace, for example, automotive applications. Then there is applications in electronic packaging, biomedical and sporting goods. So, lot of applications are coming up. See, aerospace applications, if you look at this ATR-42 which has the composite materials, and you can see that these are the areas where you have the composite materials, right, like the carbon based system here, and here also you have a carbon based system. The green parts are more prone to impacts etc. So, you have Kevlar based system there. So, you have and also some of these areas where you have Kevlar based systems, and then some parts which are not that actually critical, you have fiberglass based system there. You can see that even a simple aircraft like ATR-42 has so many composites in it. If you think of space shuttle, even more, because without composite you cannot sustain. So, you can see the temperatures that it faces, huge temperatures, like this part lowest 400 degree. As you are going towards the tip, it is increasing, it goes up to 1400 degree centigrade here, and at the back also these are the areas which is also exposed. So, 1150 or about 1200 degree centigrade. So, at such high temperature you must have composites which are like carbon composites, and you also need to have sensors embedded inside it. Look at automotive applications. Some of them are like the GM cars. It has these CFRP hoods in it, valve cover is composite, the lift gate is composite, these bodies, for example, brake calipers, steel reinforced tires, it is full of various types of composites that is there in the automotive applications. Now, one interesting thing that is coming up is called integrated vehicle health management or IVHM. This is a fantastic example where sensors, actuators, processors, everything is getting integrated in the vehicle. So, what it can do is that it can sense the change in temperature, etc. It can acquire data, transfer the data, and then it can act accordingly. And when it is acting on the situations, there are a lot of things that it can do, in terms of change of shape, in terms of change of operational conditions, and it also does the back of the system processing the moment it starts to sense. Say for example, it goes to the design, engineering and manufacturing, how the product is doing. It goes to the maintenance group, what is the condition of the system. So, this all gives us the health status of the system. And also when you are taking action, then you are also analyzing the results of this action and the health status current and the predicted one, what is going to happen in future. So, all these things together, when it comes in a composite system, it is known as IVHM, integrated vehicle health management. Talking about sports applications, there are applications of it in plate like structures like for surfing, table tennis boards. One of the most important application of smart material, one of the very first one actually came in sports structures, that is in terms of the masts, actually electronic masts in the boats, the boat that is used for various types of competitions of navigations, etc. So, these parts was first made of smart material. So, that was one of the first actually example of the smart material in sports structures. Then of course, there is these tubular structures like badminton, tennis, fishing rods, golf clubs, baseball bats, etc. There is the sheet structures which is used in golf club heads, in the hull structure, and there are other structures also like variety of vehicles, sword, climbing ropes, lines, etc., where these sports applications composites are used and also smart materials today. In biomedical applications, once again in dental applications and prosthetic devices, artificial limbs, artificial bones and heart valves, all full of smart materials. Now, when we talk about composite classification, we will actually talk about two groups, basically engineered composite and natural composite, and these things can be arranged in complex range of architectures. Of course, natural composite itself comes with a complex architecture, but engineered composites are artificially designed with complex architectures in order to derive special type of activities from them. Now, in the form of reinforcements, you can have conventional reinforcements like particles, fibers, whiskers or layers, or you can have non-conventional architectures like co-continuous system, where the fiber and the matrix develops together, interpenetrating networks, it happens in polymers, functionally graded materials, I talked about it earlier, and the hybrids where more than one reinforcements are present in the system. And in terms of architectures, if it is just that you have the reinforcements, suppose this is what is my beam and you have reinforcements only in one direction, you have it as unidirectional. If you have reinforcements in another direction, it will be bidirectional. If it is divided into small parts, then it will become discontinuous and it can have random orientation or a preferred orientation in the system. Natural composites, you would be knowing that two of the most important structural systems are actually having natural composites. One is wood, and which has lignin matrix plus hemicellulose, and another is bone, which has organic fibers plus inorganic crystals with it. Both of them are good examples of natural composites, which is worth of emulating. We will also see that we take inspirations from both of them in smart materials in terms of developing composites which can heal itself, self healing materials. We will talk about it towards the end of our course, self healing smart materials. So, that is about the natural composites. Now, when we talk about the engineering composites, then we will actually talk about fibers and matrix. They are separate from each other, we form them, and the role of the fiber, as I told you, is to improve the properties of the matrix. So, matrix on the other hand bind the fibers together, it transfer loads to the fibers and protect them from environmental attack and handling. Now, there are two main classes of fibrous composites. One is architecturally long fiber and small short fibers. Okay. So, if I go for long fibers, I get better stiffness, strength, but it is more difficult to manufacture. And unidirectional fibers are actually strong in the fiber direction, but it will be weak in the transverse direction. So, it will have high degree of anisotropy. We are talking about different types of fibers. So, let us try to go through the fibers. The most popular one is the glass fiber, okay, which is quite economic, and so very lavishly you can use it. At the same time, you will get all the advantages of the smart fibers if you actually use the glass fiber. Now, glass fibers actually consists of three different types of glass fibers. E glass fiber, which is basically electrically insulating in nature, but thermally conductive, then C glass fiber and S glass fiber. So, S is for strength, C is for corrosion and E is for electrical applications. Now, major constituent in these glass fibers are actually silica and alumina. Also, there is a bit of calcium oxide and sodium oxide. They we generally make it from the molten glass and we feed it to the platinum bushings. So, usually these all ceramic fibers are made in the same manner, and this is at a quite a high temperature 1800 degrees centigrade, and because you need to break the bonds and then you need to take the impurities out and then you need to get it out in the form of fibers. Some of the examples are NOC18-me60 fibers, which they use actually sol gel technique, and this is at a little low temperature. Then filaments which are susceptible to surface damage, that is there, that is the problem of the glass fibers. So, you need to apply something which is called sizing. Sizing is like a chemical that we apply sometimes, things like organosilicon, okay, organosilicon. So, it is kind of a silicon oil which we give, so that the fibers will not actually rub with each other or will not get in touch with the external stress concentration, so that it will not get broken easily. And the density you can see is very low, 2500 kg per meter cube. Tensile strength is good, we will not say it is very high, but it is quite good, and Young's modulus is also quite good, almost same as the aluminum. However, it is susceptible to moisture absorption and the strength decreases as a result of it. So, one has to take care of it. That is why sometimes with the glass fibers, optical fibers are also included, so that you can check what is the moisture absorption in the fibers. So, this is used in roofing, frames, tanks. There are high volume containers today, which they are actually making using the glass fiber based system, and health monitoring of such a system is absolutely essential, because otherwise if such containers collapse, that will create catastrophes in terms of storage. So, that is what is our glass fiber. The second one is not very popular, because it is very expensive to make, that is what is boron fiber. It was generally used in space shuttle type of applications, and what one has to do is that one has to actually vaporize this boron and then deposit it on tungsten ware. That is why finally, the fiber is not very thin, it is something like 75-80 microns, because it contains inside 10 to 12 micron of tungsten ware. So, however, naturally tungsten and boron together, it gives a very good property in terms of high temperature. So, you can use such composites in high temperature. Naturally, this is used in space shuttles. One of the first space shuttles are made of the boron fibers. Wherever you need a good strength and high temperature, you also have graphite and carbon fibers, extensively used in high strength, high modulus applications. Graphite fibers contain carbon in excess of 99%, whereas carbon fibers is about 80 to 95%. The more the carbon fiber, the better it is in terms of say thermal conductivity, in terms of strength, in terms of high temperature resistivities, etc. You know how you will increase this carbon content, that will depend on the processing method. There are various processing methods. I would not discuss it here. I have discussed it in Nature and Properties of Materials, just to tell that there are methods like X cellulose, there are methods like X pitch, and there are methods like X rayons. So, based on what type of material you are using to begin with, and then different processes are utilized in order to gain a good amount of carbonization of the system. So, the key applications are that, well, of course, one point you have to keep in mind, this is more expensive than the glass materials, glass fibers, and the key applications will include aerospace applications, definitely some sports applications, and to some extent railways, automotive only for sports cars, oil drilling, this type of things, the application is becoming very heavy. Source of the strength, particularly in graphite structure, that consists of the hexagonally packed carbon atoms in layers. So, that layered plate like structure, that in plane it has tremendous strength, but it is interconnected through weak van der Waals forces. Such structure will give you high in plane modulus and less modulus in out of plane direction, and a precursor material which is rich in carbon, that is subjected to a high temperature, which is called pyrolysis, which is a thermal decomposition of organic material when it is subjected to elevated temperature in absence of oxygen. That is what is the pyrolysis process. So, using the pyrolysis process, one actually carry out this kind of graphitization of a system. Now, in terms of carbon fibers, I told you that there is a precursor that is needed, okay, and very often we take actually polyacrylonitrile as a precursor fiber. The precursor is the point or the initial material from which you are actually developing the final material, the final fiber. So, PAN is one of the common one. Other than that, that pitch is one, that is the X pitch process I told you. Then rayon is another, okay, which is from cellulose type of fibers. So, there are different types of sources from which you can make such carbon fiber. When you choose the precursor material, we check that it must have sufficient strength and handling properties, so that it can hold together the fibers during the production process. It should not melt during the production process. Only thing is that all the volatile should go out and you get a fine high carbon content structure, and it should not be completely volatile, then you will not get that structure, and it should self align in graphite structure during pyrolysis. So, based on that, typically such kind of materials are chosen by people. I told you about the pan based carbon fibers, which is the cheapest of them, low cost. It has reasonable mechanical properties, and that is mostly used in aircraft, missile and space applications. For pitch based carbon fibers, it has higher stiffness, higher thermal conductivity. It is cheaper also, but it is mostly used in thermal management systems and some satellite structures. Rayon based carbon fibers, they are not much used in structural applications. It has low thermal conductivity and generally useful for insulations and heat shields. So, depending on what source you are choosing for making a carbon fiber, you are landing up with different types of, at least 3 different types of variants of the carbon fibers. There is another interesting fiber which is used to make composites, that is called Kevlar, and Kevlar is the commercial name. The actual technical name is called Aramid fiber, and this is a generic term and the commercial names are Kevlar and Nomex from DuPont, Technora from Tenjin and Boron from Akzo. So, these are developed much unlike the pyrolysis process in carbon fiber development. Here it is developed through solution polycondensation of certain materials like diamines and diacid halides at low temperature. So, temperature is low. So, that way it is easier or less expensive to fabricate, and they have a mesophase order at low temperature, and which is something like liquid crystalline form, and that we is used for in terms of alignment of the system in a fibrous form. This kind of polyamides, they have a high covalent bond axially, but transversely they are weak. So, they are actually anisotropic. So, to begin with itself, some fibers are anisotropic. So, in the composite, when you put them, the composite would definitely become anisotropic in nature, but they have high resistance to abrasion, high resistance to organic solvent, they are non-conductive, tough as well as strong, okay, and no melting point. Actually it degrades directly, that is why it does not have a melting point. From the solid state it directly degrades, gets volatile, and it has a low flammability. So, it will not burn very easily. These are some of the good points of Kevlar. This is where we have given you an overview of such composite materials. In the next lecture, we will also talk about how do you manufacture such materials, some of the techniques, and we will talk about polymer matrix composite, metal matrix composite, ceramic matrix composite and carbon-carbon composites. Okay. Also, we will discuss about some structural composites and the micromechanics of the composites in the coming lectures. Thank you very much.